Hi everyone, and welcome to our module on chemical level of organization. This class we're going to be discussing the elements. You don't need to know all the elements in the periodic table, but you need to know the elements that are important to the human body, and you need to know where are they located in the periodic table. After that, we're going to move on to study the atom. We're going to focus on the subatomic particles. And when we go to this point, the electronic behavior, this part is going to be important for the next topic, which will be the bonds. At this point, hopefully, you'll be able to understand what is the relationship with the electron's behavior and different type of bonds. We're going to review ionic bonds, covalent bonds, and hydrogen bonds. When we finish here, hopefully, you will be able to know what is the relationship between atoms and elements. After that, we're going to study the chemical reactions, and later we're going to review the inorganic compounds and organic compounds. We're going to start talking about elements, but before we get to that point, it's important that you know what is matter. And matter essentially is everything that occupies a space and has mass. Matter is everything that every substance that is present in the universe. Matter is things that are alive and things that are not alive. In our world, all the components of fundamental substance are called elements. And an element is a pure substance that is distinguished from all other matters by the fact that cannot be created or broken down by ordinary chemical means. In this slide, I have a picture of the periodic table. We can find all the elements that we know about here in the periodic table. You don't need to know or memorize all of the elements. You need to focus on the elements that are important for the human body. And just to mention some of them, you need to know where the hydrogen is located. You need to know about the carbon, nitrogen, oxygen, chloride. Also, you need to know about the iron, sodium, potassium, calcium, and magnesium. It's important to mention that all the elements in your body, they come from an external source. So they come from all the food that you eat, and they come from all the air you breathe. And we have four. Those are the four most abundant elements in the body. You need to memorize them. And the way that I like to memorize them is like the first one, oxygen, is going to be easy because that's what we breathe, and everybody knows that without oxygen we cannot live. Now, in the previous class, I mentioned that oxygen represents about 20% of the air that we breathe, and the rest, the 80%, is nitrogen and argon. You need to know about the argon. Just know that nitrogen represent about 80%. So every time that we breathe, we get nitrogen through the air that we breathe. So nitrogen and oxygen, you can remember that those two are the two of the four more abundant elements. And then the rest, carbon and hydrogen, try to remember that everything that is alive in this world contains organic compounds. So organic compounds. And the organic compounds are formed by carbon and hydrogen. In this slide, we can see a representation of what I just mentioned before. The four more abundant elements, nitrogen, hydrogen, carbon, oxygen, you can see the numbers here. The important thing that you remember is those four represent about 95 to 96% of the whole elements in the body. Now, that doesn't mean that you don't need to know about the rest, because really you need to understand and know how other elements are important for the body. And here in this table, you can see all the elements you need to know: the calcium, phosphorus, potassium, sodium, chloride, and magnesium. And just as an example, people sometimes get very sick. Let's say that somebody has very bad diarrhea and got very dehydrated, and they need to go to the emergency room. And the fluid, the IV fluid that they're going to put you to try to get you back to hydration is going to be saline solution. And the saline solution that we normally use in the emergency and hospitals contains sodium and contains chloride or chlorine. Um, so you can see how those two elements are important. Sodium and potassium also are very important in the nerve impulse transmission. Other examples of this is nitrogen. I mentioned that nitrogen and carbon form organic compounds, but nitrogen also has to do with acidity, and we're going to see this later in this chapter. Now here in this side it says symbol. You need to know the the symbols for the main elements that of the body. So many of those are easy to remember, like oxygen is an O, carbon is a C, but there's a few that are kind of tricky. So if you see this P, you might think that this is potassium, but remember that this is actually phosphorus, and potassium is represented with a K. So be careful with this. Also, if you see here sulfur, you might think, okay, S is for sodium, but really the name or the symbol for sodium is Na. So just put attention on those. The rest of the elements, they should be easy to memorize. And then other important thing that uh, there are minerals also that are very important, and there are other elements that are very small, like the ones that you can see here. They can play a role. Iron, for example, you know that people who has low iron, they tend to have anemia. So with these ones, I would say that just focus on iron at this point. Okay, so we talk about the elements and which elements are important for the body. Now, in nature, most of the time, we're going to find elements forming compounds. It's very rare to find elements in the environment that are just alone. Most of the time, they form compounds, and a compound is a substance composed by two or more elements joined by chemical bonds. Um, as an example, we have this glucose, and this is a representation of a glucose compound. You don't have to remember this structure, but I put in here just so you can know that it contains three type of elements. It contains carbon, hydrogen, and contains oxygen. And you can see here where all the carbons and oxygens and hydrogens are located. So every time you see something that contains more than one element, you have to know that that's a compound. Now, water is very small, and you see glucose is a kind of complex compound, but water is H2O, and it contains oxygen and contains two atoms or elements of hydrogen. So don't if you see this in the exam, water is a compound. Let's talk about the atoms now. Atoms, as a definition, an atom is the smallest quantity of an element that retains the unique property of that specific element. Atoms are made up of even smaller subatomic particles, the protons, neutrons, and electrons. You need to memorize what are those three. You need to memorize the subatomic parts of the atom. And then if you look here at the picture, we have two modules. We have a planetary module and we have an electron cloud module. And they're called modules because really we don't know um, how the atoms actually look like in real life. Atoms are so small, and even until today, we don't have a enough powerful microscope uh, that is able that we can see how atoms looks like. So these models, it just they are drawn this way to try to help us to understand what is or what's the behavior and what is the properties that atoms has. But um, just keep in mind that this is not real how an atom looks like. But for this class, for the purpose of this class, you have to know the structure of the atom. So we're going to start here. This is an H and E. That's the symbol for helium. That's an element in the periodic table. Helium is a gas. So this part here is called the nucleus. And as you can see also here in the picture, nucleus is everything here. So in the nucleus, we have two subatomic particles. We have protons and we have neutrons. We're going to talk about those in more detail later. But for now, just know the protons has a positive charge. And then in the electron cloud right here, we're going to have electrons. And you need to memorize how the electrons are, what's the representation or symbol for an electron, which will be this one here. It's an E and a negative. And I have a negative because electrons have a negative charge. The next thing that you need to know also is that in general, when we talk about charge or when we talk about electrical charge, every time you have two positive or two negative charge, they used to repel each other. So every time you have two of the same, they tend to repel each other. And when you have, for example, a positive and a negative, they tend to attract each other. So if we move back here to the example of the atom, we can see here. Let me use this one for here. So we can see here that we have a positive charge and we have a negative charge. So the nucleus here is positive. So that positive and that negative of the electrons make or keep the electrons close to the nucleus. Now, some of you might wonder why, if they attract each other, why they never collapse, why they never go that close to the nucleus. That's a question that is, until today we don't have an answer, and that's how mechanic quantum was born from that question. So, but in general, when you have an atom that has a negative charge and then you have another atom that has a positive charge, they are going to tend to attract each other. If there are two atoms that have the same charge, they are going to repel each other. And the same thing here, you can see that the nucleus here, it contains two positive charge. And you might wonder, well, how those two positive charge get together if similar charge repel each other. You need a lot of energy, in order to put two atoms that have the same charge together. Might talk about more detail about that later in this chapter. So far, the important thing that you need to know is that two positive or two negative charged elements, they tend to repel each other. They don't like to be together. But if we have a positive and a negative, they will attract each other. All right, let's talk about in more detail about the protons. So that's going to be the first subatomic part that we're going to be talking about. First, the things that you need to know is the protons are positive charge, and you can see it here. So that is a proton. And the other important thing you need to know is the protons give mass to the atom. That's something you need to remember. And other thing that is crucial that you need to remember is the number of protons determines the element. So really all the subatomic parts of all the atoms are the same. So the protons for one element, it doesn't change, or it's not different than the protons of other elements. And the same is true for the neutrons and electrons. All the neutrons, electrons, protons are the same for all the elements. What makes an element specific, or what makes an element is the amount of protons that they have in the nucleus. For example, helium, as you can see here in this picture, it contains two protons. So because it contains two protons, that is helium. There's not other element that contains two protons. And then if we have, for example, just one proton, that will be a molecule, that will be an element of hydrogen. So, and we can move on there, but the important concept that you need to know is that the number of protons is, or that determines which element will be. Now, neutrons, on the other hand, they have, as the name implied, they don't have a charge, so they are neutral. And you can see it here, they have no charge, but neutrons give mass to the atom. So we learned already that protons will give mass to the atom, but also neutrons will give mass to the atoms. And we're going to see that that's going to be important when we look at the periodic table and we look atomic, the atomic weight for some of the elements. Just know that the protons and neutrons give mass to the atom. And then electrons, they're so small that they really don't represent, or they're not give too much mass to the atom. So just know that the main two subatomic um, parts that give mass to the atom are the neutrons and protons. And then later we're going to mention something about isotopes. So for now, just remember that all the elements have a specific number of protons. And if that element has a different number, it's a completely different element. So if we have, for example, here, we have one proton, this is this is an element of hydrogen. And you can see here that I put a P here to let you remember that this is a proton. So hydrogen has just one proton. If we see, or if we add another proton, that will be helium. But this is not the case with neutrons. You can have neutrons uh, in the same atoms. So in general, the amount of neutrons are most of the time the same amount of protons, like we see here, like deuterium. So deuterium contains one neutron and one proton and one electron. So that molecule used to be stable. Now we have an isotope when the number of neutrons change. So if you can see here in this example, the tritium, it contains one proton but contains two neutrons and the same amount of electrons. And the first one, we can see that there's just one proton, no neutrons. Um, we have one electrons. We're going to talk about isotopes later. For now, just remember that isotopes has to do with neutrons. Finally, we're going to talk about the electrons, which will be the last subatomic particle. Remember that electrons has a negative charge. Um, they exist in a cloud or in a shell, depending on which model you use. In the planetary model, this is the shell, and in the cloud electron cloud module, this is the cloud. Now, remember that those modules, they just help you to understand the behavior of the atom. Don't look like, in real life, they don't look like this. And then other important thing that you should know is that in general, the number of electrons in an atom are equal to the numbers of protons in an atom. So if we look here at the picture, we have helium, and helium has two protons. So helium in general will have two electrons. And that's true for the rest of the elements. Like, let's say carbon. Carbon contains six protons, and in general, it will contain six electrons. Those electrons might change when these elements interact with another, but for now, just as a general rule, remember that the same amount of protons usually is the same amount of electrons. And lastly, electrons, as I mentioned before, they're very, very little, and you see here that it just represents 1 in 2,000 mass of the proton. In other words, you will need 2,000 um, electrons in order to complete the mass of one proton. So they're very little, and for that reason, the electrons do not contribute to the mass of the atom. Okay, so now we're going to talk about um, the atomic number and the atomic mass number. And those are going to be important that you understand because in the exam, you might be asked to find atomic number for X element or the atomic mass or atomic weight for X element. So it's important that you understand those two concepts. I mentioned this already that the elements are defined by the numbers of protons inside of the nucleus, and I gave you the example of carbon, which contains 6 protons, and that's what made the carbon be carbon because 6 protons. Now, the atomic number is the number in the nucleus of the atom, and that number identifies the element. So when you go to your periodic table, you're going to see all the elements, and then you're going to see a number in the superior left side, and that number you find there is the atomic number. So if, for example, you go and look at periodic table and look for carbon, you're going to see the number 6. And with that, you know that that element contains 6 protons. If you look sodium, for example, in your periodic table, you will see 11. That let us know that sodium contains 11 protons inside of the nucleus, and so on and so forth for the rest of the elements. Let's mention oxygen, which also is important, is the number is 8. The atomic number is 8. So you know that atomic number is the number of the protons, and oxygen is oxygen because it has 8 protons. Now, the other concept you need to know is atomic mass. Earlier, I mentioned that protons give mass to the atom, but also neutrons give mass to the atoms. So the mass number or atomic weight, you also can find that in the same. Um, it will be it will be the sum of the number of protons and neutrons. Now, remember that in general, we said that protons and neutrons usually are the same, but uh, in some elements or in some isotopes, you're going to find more neutrons than protons, and that will change the mass number. And I bring here again the periodic table picture so we can see some examples. So I mentioned early carbon. The atomic number for carbon is 6. It contains 6 protons. And in general, an unstable molecule of carbon will contain 6 neutrons. So the atomic weight or the mass is 12. And hopefully you should be able to see it here. It's very small, but it's 12. And you can check all the other elements. Nitrogen, it has 7, and in general, 7 protons, 7 neutrons will have an atomic mass of 14. Oxygen, same thing, 8 protons, uh, and if you see here, the atomic mass is about 15.9, which it will be 16. So that means that this oxygen contains another 6 neutrons. And however, there are other elements that they might be different. Like if we see something that is very heavy, like this 92, uranium. You probably heard about uranium and radioactive or bombs or stuff like that. So you know here that the atomic number of uranium is 92. So that means 92 protons. But if you look at atomic weight, uranium is 236. That means that that molecule of uranium contains 92 protons and 146 neutrons to make a total of 238 atomic weight or atomic mass. Now we're going to talk about in more detail about the isotopes. When you see the word isotopes, remember neutrons. And then finally, we're going to talk about more detail about electrons and how the electrons behave. I mentioned earlier that atoms can have different numbers of neutrons, and when that happens, that specific element are called isotopes. So isotopes, one of the different form of an element distinguished from one another by different numbers of neutrons and nucleus. And we use the example of the hydrogen, which it contains in, you can see it's still hydrogen. This is still the element of hydrogen, but it contains, this one contains just one neutron, this one contains two neutrons, and this one don't have neutrons. The important thing that you need to know about the isotopes for your exam is that isotopes tends to be unstable, especially those isotopes that have more neutrons than protons. In the example, the hydrogen example, the hydrogen that contains one proton and contains one neutron, that's usually the stable version of the hydrogen. The one that contains two neutrons are more unstable. And then other thing that unstable isotopes, they tend to have radioactivity properties, or they used to be radioactive. Now, as you probably know, radioactive can be very harmful or it can be very dangerous for life. But in medicine, we use those isotopes in our favor sometimes to diagnose diseases or just to use in different tests. So I put here in this picture, this is as an example of a PET scan. PET scan stands for positron emission tomography. And the way that this test works is that the patient, we put an IV glucose. Remember, the glucose is a type of sugar. And that kind of sugar that we put is an isotope sugar. And we inject the sugar into the body. And we have a machine that we can see and picture where that glucose is located. Now, people who has tumors or cancer cells, those type of cells are replicating and multiply, and they have a very high metabolism rate. So they're using a lot of sugar. So the sugar that we inject, that is an isotope, used to be bright when we look at the test. So here, for example, in this picture, we can see here, this is the heart, but the heart always is beating, so that's normal. But we can see here in this other side, we don't really have something here, and there are cells that are taking that radioactive or that isotope glucose that we inject. So that might be cancer cells, and we can see it here in this picture. We can see here in this other picture that this man, he shouldn't have a lot of metabolism going on in that side. So that helps us to know where sometimes metastases or where tumors are located. And then we also use something that's called radioembolization. And radioembolization is we use another type of isotopes to treat tumors. Let's imagine that this is a tumor. And tumors need blood in order to grow, in order to get oxygen, we need blood. So what we do with radioembolization is we inject um, an isotope that is radioactive, and because it can be hard, it can cause damage to the cells. That isotope usually is injected here and cause damage of the vessels that provide blood to the tumor, and eventually the tumor cells will die because radioactivity. Now let's talk about the electron behavior and how they are related when an atom or an element interact with another atom to form bonds. So it's crucial that you understand the electron behavior to understand the bonds. We mentioned earlier that atoms are constantly reacting with another atoms to form a complex substance that we call compounds. And it's very rare to find an atom just alone. Most of the time, they form substances. So the key to understand those reactions between different atoms is understanding the behavior of the electrons. So to do that, we're going to need to understand two concepts. What's the electron shell and what's the valence shell? So if you look here at this picture, we have four different atoms. We have hydrogen here, we have helium, and we have carbon, and we have neon. The blue dots, at this point, you know that those are electrons. And you can see here that this is the planetary module. That's the module that we're going to use to try to understand the electron behavior. So this first like kind of orbital shape is called the electron shell. And you can see here one, you can see here all this one, and you can see that neon contains two, one here, one here. Carbon contains two, one here, one here. And I'm going to talk in more detail about the electron shells in a minute, but for now, just remember that the first electron shell, which is this one here, it can only contain just two electrons. It cannot contain more than two. If an atom like carbon has more, after he complete this electron shell, the other electrons are going to be moved to the second level of energy or to the second electron shell. In this case, this is the second. And as you can verify this in your periodic table, the atomic number for carbon, we said it was 6. So you can see the 6 in general, carbon will have 6 electrons, and we can see 2 here, and then 2 here, and 2 here. So that will be 6. And that's the same for neon. Neon, we have 2 here, and then we have 1, 2, 3, 4, 5, 6, 7, 8. So the atomic number for neon is 10, and you can verify this in your periodic table. So those are called the electron shells. Other important thing that you need to know about the electron shells is that the second electron shell can hold 8 electrons. It can hold 8. So for example, if we look at here at the neon, so the first electron shell is full because it can only hold 2. The second electron shell is also full because it has 8. 1, 2, 3, 4, 5, 6, 6, 8. So if we add, for any reason, if we add another electron, we will not be able to put it here. We'll have to have another energy level or another electron shell in order to put more electrons, and we're going to be able to put 8 electrons more. Now, what is the valence shell? So the valence shell is an atom's outermost electron shell. The number of electrons in its valence shell strongly governs the tendency of an atom to participate in chemical reactions. If the valence shell is full, it's stable, it's unlikely that it's going to react with other atoms. If the valence shell is not full, the atom is reactive, so it probably will react. And if you look here, this picture, we have the example here, sodium. Sodium contains 9, and you can see that the atomic number, I'm sorry, 11. Then you can see that the atomic number for sodium is 11. So we have 2 here in the first electron shell, that's full. The second electron shell is full as well. And then we have a third one. And in this third one, we only have 1 electron. So as a general rule, atoms or elements, they want to complete their valence shell to 8. That's the tendency that they have. So for example, if we look here, the sodium, this atom will love to either gain 7 electrons or maybe just remove 1 and stay here in the second shell with with this completely full. So, but what do you think is going to be more easy for this? I mean, it's going to be very hard to find 7 electrons. So it's more easy for this atom just donate this electron. And when he donate this electron, you can see that his valence shell will be complete. We'll have 2 here, and we will have 8 here. And this atom will be more stable. Now, other thing is that I hope you can appreciate here, once this atom donate this electron, electrons has a negative charge. So we're taking or removing negative from this atom. So after that happened, you can see here that the sodium now has a plus, and then it has a plus because he lost some electrons. And so elements that it has tendency to donate electrons usually are going to have a representation of a positive because they tend to donate the electrons. They get rid of negativity and they become more positive. Now, if we look the other example here, this is the chlorine. We have a chlorine, we have 2 plus A, that's 10, and then we have 7 chlorine, atomic number is 17. So you see here this is the valence shell, and if we look here, this is the electron shell, and this is the electron shell. The definition of a valence shell is the outermost, so will be all these here that I'm drawing. That is the valence shell. And it's important also, I want to take this opportunity to explain this, that because the nucleus is positive and all the electrons are negative, they tend to, or they want to be close to the nucleus because they are attracted to the nucleus. So the valence shell is important because the electrons that are in this electron shell, in the valence shell, they're more far away of the nucleus, so it will be easy to remove electrons from here. They try to remove an electron for here, for example. You will need way more energy in order to remove an electron that is closer to the nucleus. So that's another thing that is important. You remember that's why the valence shell is so important for reactions, because it's the weakest part of the electron shell that electrons can be donated or can be added. So going back to the chlorine, we said that chlorine has 17. So it will be way more easy for the chlorine to receive an electron so he can complete this valence shell and be more stable than just donate donate 7 of them and keep there. So because of this, the tendency is that chlorine will receive an electron, and because the fact that he's going to receive negativity, this chlorine is represented with a negative here. And finally, when we mentioned that when we have a positive and a negative, if we look all this is a whole element, and this is a whole element, and this element overall has a positive charge, and this element overall has a negative charge. They tend to attract each other and start forming compounds, and we're going to see later an example of these compounds, and when they 2 elements or atoms uh, uh, bond each other, they will form what we call ionic bonds. And this is just a recap that what I just mentioned. That first, that all the number of protons will determine the atomic number and will determine which element is. We mentioned that sodium, for example, it contains 11 protons, so the atomic number is 11. And in general will contain 11 electrons, but as you saw previously, um, sodium tends to donate one electron. So when they donate that electron, he will actually have 10 electrons instead of 11. But in general, the same amount of protons, you have the same amount of electrons. And this is the distribution that we just mentioned. And this is the same thing with oxygen. You can look this in, with more time when you're studying. Now that we understand the electron's behavior, let's talk about the bonds. Before we talk about bonds, let's just recap what a compound is. We said that a compound is made up of two or more atoms of different elements. And that's the key word here. So when we have a compound, we have two elements that are different. Like water, for example, it has hydrogen and have oxygen. And this that is methane is we have carbon and we have hydrogen. A molecule, on the other hand, is a grouping of two or more atoms held together by a chemical bonds. Most of the time, a molecule is made by the same kind of element. So oxygen, for example, here the oxygen gas, we have a number 2, which means that there are two oxygen together. And the same thing for the hydrogen. There are two hydrogen atoms linked together. Now, when one molecule or when a compound, the way that they are linked together is through bonds. So bond is a weak or a strong electrical attraction that hold atoms in the same vicinity. The new group is typically more stable, and when it's stable, they're less likely to react again. And we're gonna see three types of bonds. We're gonna review the ionic bond, covalent bonds, and hydrogen bonds. You need to remember and you need to know each bonds for your exam. Now we're going to see ionic bonds. So in order to understand ionic bonds, we need to understand first what is an ion. So an ion is an atom that has an electrical charge. And it could be a positive electrical charge or it could be a negative. And if it's a positive, it's called cation. And if it's a negative, it's called anion. And the way that I always remember this is if you look the word cation, it contains a T here, and the T looks like a positive. So that helped me to remember that cations are positive charge. Examples of cations, we have the potassium, we have calcium, and we have sodium. Now, you're going to see here that calcium, for example, contains 2 plus. And what does that mean? Is that the calcium is very positive, and we can see this here. Now, this is a chloride, so let's pretend that this is calcium. So the atomic number for calcium, if you look, is 20. So that means that calcium contains 20 electrons. So here we know that chloride contains 17, so we need to add another one. So we have 18 here. That means that to go to 20, we need 2 more electrons here. So that will be a 20 electrons, so because it's calcium. Now, with what do you think is going to be easy for this atom? It will be easy to try to find 6 electrons more to complete the valence shell, or it will be easy for this atom just donate those 2 electrons so that way he can complete his valence shell. So because it's easy to donate 2 electrons, the calcium will be likely to donate 2 negativities. So because he is donating negativities, he's becoming more positive. And that's why calcium contains 2 plus when you see the representation of calcium, because it tends to donate 2 electrons. And when calcium donate negativity, become a positive ion. And positive ions are called cation. And then we can see example of anions with chlorine or chloride, and that molecule is carbon dioxide. And I mentioned before that opposite charges they exert a moderately strong mutual attraction. So if we move here to the example, we have a positive, we have a negative, they tend to go and attract each other. Now it's important, and when they do that, they form what we know as an ionic bond. Now, the important thing that you know about this is that electrons in ionic bonds, the electrons may be donated or accepted. That's crucial that you remember this for ionic bonds. And the other thing that is important is that water can break ionic bonds. And every time that there's ions forming compounds like sodium and chloride, they will form salt. So in this case, when we have an example of sodium and chloride, we got table salt. But there's another ions that can form ionic bonds and will form different type of salts. Now let's talk about covalent bonds, which is a different type of bond. In covalent bonds, the atoms in the molecule do not donate. That happen in ionic bonds. Here uh, they do not donate. They instead they share the electrons in a mutual stabilizing relationship. I told you that atoms they love to have the valence shell full, so they tend to either donate or receive electrons, or in this case, in the covalent bonds, they will share in order to complete their valence shells. And we have two types of covalent bonds. We have the non-polar covalent bonds, and then we have the polar covalent bonds. We're going to see this, each of these in more detail, but in the non-polar, the sharing of the negativity electron is equal as the electrical pull of the positive protons in the nucleus. So overall, they don't have an electrical pull. And you'll will understand better this when we look at pictures. In the polar covalent bonds, the sharing of the negativity electrons is unequal, and we're going to have here a positive electrical pull and a negative electrical pull. So in this slide, I have an example of a non-polar, and I have an example of a polar covalent bonds. So if you look here in the picture, in this picture, we have an example of two hydrogen atoms making a molecule. And you can see here that this part of the hydrogen, this is the nucleus and had a positive charge. And this is the other molecule, it had a positive charge. And they share the electrons. Remember that hydrogen normally just contains one electron in the first electron shell. In this case, this is also the hydrogen valence shell. So hydrogen will love to have another electron in order to complete the valence shell. So in this case, he shared with another hydrogen atom. So this hydrogen atom contains two electrons because now they're sharing, and this one contains two. And overall, the molecule is the electrical charges are perfectly uh, uh, balanced. We're going to see that better in the example number 2. So here we have a molecule of O2 or oxygen gas, and this is other way to represent the other way that we can represent this. So in here, what I want you to look is that in the nucleus we have a positive charge, and we have a positive charge, and all these dots are electrons, so they're negative. So look at here that this side of the molecule, it contains 5 electrons, and then the other half of the molecule, it also contains 5, and I take those two because those are the electrons that this molecule is sharing to this one to complete the valence shell. So you can see that in both sides the negativity is equal, the distribution is equal. And if we look and the other side is also the same. So um, we'll here 5 electrons, and then again we're going to have 5 electrons here. So that makes this molecule perfectly balanced. And also we can see that the positive charges are also perfectly equal. So when there's that equal, they're not electrical pool, so this molecule is non-polar because they're not electrical pool. There is not a part of the molecule that is pulling or having more negativity or more positive. And we can do the same thing with CO2, which is carbon dioxide. You can see here the same example. We have 5 electrons and we have 5 here, which it kind of balances out. And so at the end, this molecule it has not pull, so it's a non-polar. If we look the example of a polar, we're going to see here water. So H2O. We have a molecule of water who contains, a compound that contains 2 hydrogens. And we have a hydrogen here, we have a hydrogen here, and then we have oxygen in this side. So in this case, you can look at the electrons distribution, and you can see that we have in this side of the molecule 6 electrons. And then in this side, we only have 4. So therefore, we have more negativity in this side of the molecule. And you can see that negativity reflected in this picture. So we have here, this is the delta. That means that there's a partial negativity. And the reason that this part of the molecule is more negative is, as you can see in the picture, that has more electrons there. And if you look here, in this side, the hydrogens they have more relatively positive charge because the electron has been pulled by the oxygen molecule, and this part of the molecule is more positive for that reason, and that molecule is on a polar uh, covalent bond. Then the last bond that we're going to see is the hydrogen bond, and this is simple. The hydrogen bonds is formed when a weak positive hydrogen atom already bonded to a one electronegative atom is attached to another electronegative atom from another molecule. Pretty clear, right? So really what all this means is that hydrogen atoms form when 2 molecules link together and have partial positive and partial negative charge. And the important thing that you need to know about the hydrogen bonds is that usually they're weak, and that's the reason why you see the dots kind of in this way instead of being a whole line. Is because the bonds are more weak, and sometimes we can see example of hydrogen bonds in proteins, and as we're going to see later in this chapter, when proteins lose their hydrogen bonds, they tend to unfold, and that cause damage in the protein. But for now, just remember the hydrogen bonds are bonds that are relatively weak, and there is hydrogens unions. In this case, we have a hydrogen that is linked to the negative part of the oxygen. Okay, now we're going to talk about the chemical reactions. And after we finish this part, I will suggest you take a break because we are already covered a lot. It's been almost an hour. And so we're going to go here discuss the energy that is in the chemical reaction, what are the characteristics of the chemical reaction, and the factors that influencing the rate of the chemical reactions. So if you remember in the previous chapter, we talked about metabolism and why metabolism was so important, because it's the sum of all the chemical reactions that go to maintain an organism's health and life. And we need to discuss why we need energy in the chemical reaction and what is the role of the energy. So we need to understand some basic concept about energy. The first concept you need to know is for your exam is to know what is the kinetic energy and what's the difference between kinetic and potential energy. So kinetic energy is the form of energy powering any type of matter in motion. For example, somebody who is building a brick wall, the energy that the person is using to place the brick on top of another, that is considered kinetic energy. And then potential energy is the energy of position. Um, in the example of the brick wall, all the bricks that now has potential energy that can get released as kinetic energy when they collapse. So if we can see this picture here, let's imagine this is the ground and somebody is putting blocks here. So he's using kinetic energy to make a wall. Now this wall here will contain potential energy because if this brick fall, will make a movement. And kinetic energy is about motion. So, and as you can imagine, if this brick is very, very high, all the energy that you use in order to put that brick at this position, uh, it converts this energy or is retained in a way of potential energy. And the potential is because it has the potential to release energy in some way. And in the chemical reaction, they're not going to work like this in this example, but the chemical energy is stored in chemical bonds. And we discussed already what a bond is. So the energy will be stored there. And when those bonds are formed, you need energy to form those bonds. But the energy that you invest forming the bonds will still be there. So if we, for example, have a molecule of ATP, which is the molecule that we use to get energy, initially this molecule might contain just two uh, phosphate groups. So when we add another group and we make another bond, it will become ATP. We need energy to form this bond. But in the same time, when we break that bond, that energy that is containing in the bond as a potential energy will be released and will become kinetic energy. So hopefully with this example, you have a better idea what is a kinetic and what is a potential energy. Now let's talk about in more detail about the characteristic of chemical reactions. Every time that we have a chemical reaction, we essentially need a reactant and we're going to have a product. So a product and a reactant. The reactant in general terms is used for one or more substance that enter into a reaction. In this case, if you look here, this picture, nitrogen and hydrogen are reactants, and they're called reactants because they're going to enter in a reaction. And products, on the other hand, is one or more substance produced by the chemical reaction. If we look back here, we see the product, and this arrow here represents the movement of the direction of the chemical reaction. Now, there are three fundamental chemical reactions that you need to know for your test, for your quiz, and for your exam. You need to memorize this. The three fundamental chemical reactions are synthesis reactions, decomposition reactions, and exchange reactions. And then other thing that also you need to see in this example is that when you have a product, most of the time uh, you're going to see chemical reactions that are reversible. So in this case, is we can still move from this to there and basically go to the starting point. And if you remember the concept that we saw initially in chapter 1, when we add small pieces or a small substance to form something bigger, this is an example of um, anabolism. And when we start from a complex or big substance and then we make small ones, this is an example of catabolism. Catabolism, you're going to see that catabolism and the chemical reactions also are very similar to decomposition synthesis. Um, and then again, I bring again this example, and hopefully I'm just keep bringing the ATP because I want to make sure that this molecule, this molecule is very important. And this is the same concept. So we have a molecule ADP. It's called ADP because we only have two phosphate groups, and we have adenosine molecule here. So when we add another phosphate group, we need energy. This is the direction of the reaction. And then the product will be ATP. And you remember that in chemical reaction, we have this energy in the bonds and is stored in a potential energy. Now, when we break these bonds, the energy will be released and will transform to kinetic energy. Every time we break this, will be kinetic energy that the body will use to function or make any specific function that he needs. Now here I'm going to go very quick because this is kind of the same. Synthetics reaction, we mentioned that this is an example of anabolic. And we can see here we start with two small components or reactants, and we're going to form a product here. We mentioned that decomposition is the equivalent to catabolism, and at the end we start with a product. We're going to end with the small particles or substance. Now, the example of exchange reaction, in this case, I want you to look at the general equation, and we have a substance, we have another substance that's a little bit more complex, but as the word imply exchange, it means that the product will look different. So we see A here, and then we see BC. The product will be this B, it goes here, and the C is alone. So just know that exchange reaction is just kind of exchange. This part is very important that you understand for your test. Um, what are the factors influencing the rate or the velocity of the chemical reactions? So we have four major factors that influencing the rate of the chemical reaction. First one, the properties of the reactants. If the reactants are highly reactive elements, so the elements proceed more, the reaction proceed more quickly. And if the element is less reactive, the reactions are slower, they're lower or slower. If we have temperature, so temperature is another factor. Nearly all the chemical reactions occur faster when we have higher temperatures. And then concentration and pressure, an increase in the concentration and increase in the pressure will increase the rate of chemical reaction. And finally, the catalyst or enzyme. I need you to remember this one because this is the more important. And it's more important because in our body, all the chemical reactions, the way that we accelerate or that we make reactions faster is through this mechanism. We cannot increase chemical reaction through temperature because, as you remember, our temperature is 37 degrees Celsius or 98 Fahrenheit. So normally at this temperature, uh, we really cannot improve velocity in the chemical reactions. So we cannot account with this. The properties of the reactant is not super important inside of the body. Like there's gonna be uh, play a crucial role in the influence in that. And the pressure and concentration in our body is not enough high to make chemical reaction keep going fast. So really the mechanism that the body uses to increase chemical reactions is through catalysts. And the more important catalyst you need to know is the enzymes. So catalyst is a substance that increases the rate of the chemical reaction without um, itself undergoing any change. And as I mentioned, enzymes are the more important. Okay, now we're going to talk about the inorganic compounds. We're going to focus in water, salt, acid, bases. We're going to talk about the pH and the buffers. There are way more inorganic compounds, but those are the more important for the human, and they're the more important for your test. Now, in general, both inorganic and organic compounds are essential to human functioning. The inorganic compounds are all the substance that does not contain carbon or hydrogen. An example of this is water, hydrochloric acid. This is the acid that we have in our stomach. CO2 is another example. Organic compounds are substances that contains both, and as mentioned earlier, carbon and hydrogen. They are synthesized via covalent bonds within living organisms. And the example of organic compounds we have is sugar, proteins, lipids, and nucleic acid. We're going to see those in more detail when we go through the organic compounds. Now we're going to move and talk about the inorganic compounds first. So let's begin with water. Water is an essential inorganic compound of life. It's also known as the universal solvent. If you remember when we were talking about covalent bonds, we talked about water, and we said that water is a polar um, compound that has a negative charge here and that has a partial or positive charge here. Now, it's very important that many of the substance in the body will need to be dissolved. And the better example you can get is that uh, all the elements that we need and all the substance that we need in our body needs to be transported in for some mechanism. And the mechanism that we use is through the blood. The vast majority of the blood is water. So we're going to see later, and I'll keep mentioning how important is that when substances are polar or non-polar. Then water also represents about 90% of an adult body weight, and that 90%, most of that water is inside of the cell. This is important. Ionic and polar covalent compounds dissolve in water. And when they dissolve in water or when they are polar, those substances or compounds are called hydrophilic. Hydro means water, and philic means that they like it. So, and in this case, it means that they dissolve well in water. Nonpolar compounds, on the other hand, they do not dissolve in water, and they are called hydrophobic. Hydro, again, water, and phobic means just think about when you say I have a phobia or have something that scares you. In this case, it means that will not dissolve or they don't like water. And we have some examples here of hydrophilic substance and hydrophobic. So hydrophilic, all the sugars or carbohydrates are hydrophilic, or in other words, dissolve in water. If you put sugar in a glass with water, you're gonna see that with time that completely dissolve. All the proteins are hydrophilic, and some amino acid are hydrophilic. Now, hydrophobic lipids or fat. When you see the word lipids, think about fat. Oxygen, the oxygen that we breathe is insoluble. So, and the same thing with the carbon dioxide. So we need those compounds cannot go in the bloodstream free. Like, for example, carbohydrates, because they're polar and they're hydrophilic, they can be transported free into the blood. Proteins can be transported free into the blood, but lipids and oxygen and some amino acids, because they are not soluble, they need some sort of mechanism in order to get places, or they need a, I would say, transportation in order to get from one place to one place. And we're gonna see that when we go and see lipids in more detail. So for now, just know that fats are hydrophobic, oxygen, CO2, and some amino acid are hydrophobic. And then the water, it plays many roles and has many functions. Here, there we have just one of the more important. Water plays a role, or it functions as a lubricant and cushion. So lubricants decrease friction in synovial joints, the pleural space in between the abdominal organs. And the word cushion, we can remember that in our head we have, let's say that this is a man, and we have our skull, and we have the brain here. So we have water here that it helps to cushion, uh, it helps with cushion when we move the head, or when we have rapid movement, or we have um, a contusion, or if we have a trauma. That water will kind of help to absorb some of that uh, energy, or some of that trauma. Then the water also plays a role in heat sink, and because the concept of heat sink is a substance or object that absorb and dissipate heat but does not experience a corresponding increasing in temperature. That happens with water. Water is the main way in which we, if the temperature inside of our body gets too high, we sweat, and what we sweat is water. That heat can go in a molecule of water and can be released through the skin and sweat glands. And then finally, water, of course, is a component of fluid mixtures. And the important thing here is that, that the different kind of liquid mixtures in the body, we're going to see solutions, we're going to see suspensions, and colloids. And solutions are things that completely dissolve. Like an example, you put water and you put salt, the salt eventually will dissolve completely. Same thing with sugar, and you're gonna see, or you're gonna have um, something that is completely homogeneous. And then suspensions is things that with the time you're gonna have a sedimentation, like for example blood, because it has solid part. If you put a blood in the test tube, with time you're gonna see a sedimentation. So that's an example of suspension. And a colloid is something that is not. It contains a lot of um, uh, big particles, uh, and they're so big molecules that even though they're dissolving water, they tends to appear like uh, in a different or more dense color. And an example of a colloid, for example, is milk. The milk is perfectly um, dissolved, but it tends to have that white color, and that's because it has molecules that are big. So other example of colloids are in the thyroid gland. We have uh, a colloid fluid that also it has this characteristic. Another function of the water is when the water plays a role in the chemical reactions. We're going to see that we have two reactions that has to do with water, and the first one is the dehydration synthesis reaction and then hydrolysis reaction. In the dehydration synthesis, the D means that we're going to remove water, hydration. So dehydration, we don't have, we kind of remove water. And here, what I want you to look here in this example is that we have one monomer and two monomer. The word monomer just means that there's is a molecule, is the simple molecule it can be. So if we translate to the real life example, let's say that this is a monomer of glucose. So glucose is the simple sugar. It cannot be break down further than that. And if it breaks down further, it is not a sugar anymore. So this is the basic, like brick block, if you will. And then let's say that we have a galactose, which is another simple sugar. So you can see here that those molecules, glucose, we have a chemical structure, but in one side is going to contain, and the same thing for galactose, they're going to contain hydroxyl group. This HO is called hydroxyl group. And in the dehydration synthesis, what we're going to see is that in order to link those molecules together, we need to remove water. So we're going to remove one hydroxyl group and we're going to remove one hydrogen from the other one. At the end of the reaction, we're going to end having two hydrogen and one oxygen forming water. And then we're going to see here that now the molecules, the monomers are linked together in a covalent bond. So remember that this is a dehydration synthesis. Now the other one is completely opposite, hydrolysis. And in hydrolysis, we have already a compound. We have, this will be, instead of being a monomer, this will be a polymer because it contains two or more. So in this case, in order to break this bond down, we need a molecule of water. So because we're breaking a bond, that's what is called hydrolysis, because we're breaking a molecule of water. So hydro is water, lysis is breaking. We're going to invest a molecule of water to break a bone. So here you can see one molecule is going to form the hydroxyl group, and then the other one, hydrogen, will attach to the other part of the monomer. Now let's talk about salts. Salt, as I mentioned earlier, uh, salts form when ions form ionic bonds. And we can see here in the example that we used earlier, the table salt. We have a sodium ion and a chloride ion. They link through the ionic bond and form salt. So, and the important thing here is that all the ionic bonds dissolve in water. So when they dissolve in water, the rule is that they dissociate in ions that are different than hydrogen and different than hydroxyl. This is called a hydroxyl group. So the rule here is that if there are salts, when they dissolve in water, the ions, it needs to be different than hydrogen or different than hydroxyl. If we keep looking this example, when this molecule, when this salt dissolve in water, we're going to see sodium ions attached. And you can see the sodium has a positive charge, so the oxygen charge of the oxygen is the one that's going to attach to the positive, because we mentioned that opposite charges attract each other. And then we can see here in the chloride side that this is a negative charge, and this is the relatively positive charge of the hydrogen in a molecule of water. So the positive and the negative can attract each other. So that's the rule for salts. If they dissociate in hydrogen, we're going to see later that that's going to be an acid. And if the elements, when they dissolve in water, dissociate in hydroxyl groups, there's called a base. For now, just know that it's a salt if they don't, form hydrogen or hydroxyl groups when they dissolve in water. And examples of salts that we have in the body is the bile salts that it helps to break apart fats when we eat, and then the calcium phosphates, also they're salts, and as you probably hear or know, they are an important part in the bone and the teeth. Now let's talk about acid, bases, pH, and buffers. I think we need to talk about all those three because they are related. Now let's talk about acid and bases. So let's begin with acid. Acid is a substance that releases hydrogen ions. And I want you to put attention that this ion is not like a regular ion. It contains a plus. So that means that it contains this a positive charge because it's a simple proton. Let's look here at the example. So we have an acid, and then we have water. When then the acid dissolves in this solution, it will release a lot of those hydrogen atoms. Now, early we mentioned that hydrogen contains one proton in the nucleus, and it contains one neutron in the electron shell. So, but if you look here, an acid will release a single proton. In other words, this proton here will have no electrons, and because the nucleus is positive, that's why this hydrogen is represented with a positive, because they're not an electron that make the molecule neutral. So the hydrogen will be positive. And then the other key information that you know is that acidity, it has to do with the amount of hydrogen ions that are present in that solution. So if you have more hydrogen atoms here, if you have more of them, more acid or more acidic is the solution. And that's going to be important when we talk about pH in a minute. Now, acid, we can divide acid in strong and weak. And the difference is that strong acid will release all their protons, and weak acid will release all the protons. Now, because also notice, I hope you noticed that I used the word protons when I was referring to this, and instead of saying hydrogen, and the reason what this is called a proton is because it don't have electrons. So a single proton is a hydrogen ion. Now let's move to the base. So the base is a substance that releases OH, or a hydroxyl group, and you're gonna release hydroxyl group or accept hydrogen or protons already present in the solution. If we look here at the example, we put a base, we put water, it dissolves, and it's gonna release hydroxyl groups. Now that we know what is an acid and a base, let's talk about pH. And the pH, we're going to see that the relatively acidity or alkalinicity of a solution can be indicated by the pH. The concept of pH, it might sound confusing, but I'll explain it in a minute. So the pH is the negative base logarithm of the hydrogen ion concentration in a solution. And the important thing that you know that is key for your test is that you know that 7 is considered neutral, and the human blood is around 7.35, 7.45. Now everything that is above 7 is a base or alkaline, and then everything that is below is acid. So if we look here, you're going to notice here this is the scale of the pH. It comes from 0 to 14, and half of that is 7. 7 is neutral. Like the blood is a little bit, you see that the blood is a little bit alkaline. It's just a little bit, but overall is uh, more close to neutral. Now, pure water is completely neutral. And other thing that you need to know, and we mentioned, is it's called the negative base 10 logarithm, because if you move down, like, everything down here is negative and anything up is positive. But if you move down, you see the number and you want to know, you have 7 as a neutral. 6 will means that a solution that had a pH of 6 is 10 times more acid than a solution that had a pH of 7. If we keep moving down, we can say that a solution that had a pH of 5 is 100 times more acid than a solution that had a pH of 7. And why is 100? Well, because 5, when a solution that have a 5 is 10 times more acid than 6, and 6 is 10 times more acid than 7. So you multiply 10 by 10, 100, and you can do that going down here. For example, um, a pH of 4, it will be 1,000 times more acid than a pH of 7. You just multiply 100 by 10, and so on and so forth. So overall, the important thing about the pH scale is that you know that the number, if the highest the number is base or alkaline, and the lower the number is more acid. And then this is the confusing part, but hopefully with the example that I show you, all that has to do with acidity, it has to do with protons. So when you have more protons, that means the solution is more acid. And the pH scale will reflect a number that is low. So we mentioned 6 and 3. So 3 is way more, even though the 3 looks like a number smaller, but that actually means there's way more acid than 5 and 6. And the same thing concept for the base. Now, in this picture, you can see here, the important thing about, you don't have to learn what is the pH for all this, but you have to know the concept that knowing that the neutral pH is 7, if I ask you, for example, for grapefruit, it has a pH of 2.5, so that is moderate acidic. Coffee will be slightly acidic. And if we move to the other side, seawater is 8, and that will be slightly alkaline. Pure water is neutral. Now let's finish inorganic compounds talking about buffers. We talk about acid, base, we talk about the pH. We're ready to go and talk about buffers. So all the cells in the body depend on homeostatic regulation. And if we move to the example of the pH, the body needs to be, or the blood needs to have a pH um, around 7.4. And the body uses different mechanisms to try to keep this 7.4. So there's many things that can increase the pH, and there are many things that can decrease the pH. But the ways that the body tries to compensate all those same changes is through breathing, urinary secretion, and through buffers. And buffer is the one that we're going to look now. So buffer, the definition of buffer is a solution of a weak acid and its conjugated base. Buffers can neutralize a small amount of acid or bases in the body fluids. And the better buffer example that we can have here is the carbonic acid and bicarbonate. And here I'm going to go a little bit to the chemistry, but just to give an example, you don't have to memorize all these, but let's put an example that your pH normally is 4.3. So then it goes, for some reason, let's say that it goes down. Your pH goes down because you have a lot of diarrhea and you're losing a lot of bases through the diarrhea. So your pH goes down And remember, the pH is the amount of hydrogen ions in a solution, so in this case, the blood. So when the pH goes down, that means that your concentration of protons or hydrogen ions is high. So your pH is more acid, or in the scale of pH, that will be a number that is low. So let's say that your pH goes down to 7.3. So the body needs to go back to the point that is normal. So what we're going to use here, we need to use bicarbonate, because bicarbonate is this is the formula of bicarbonate. And the thing here is that when bicarbonate is in a water or is in the body fluid solution, it tends to pick more hydrogen. So when we combine bicarbonate with a proton, remember that when we have this acidity, we have too much protons. So when we combine these, we're going to have carbonic acid. So, and carbonic acid is a weak acid, but the point here is that bicarbonate is a compound that will take the protons from the blood and form a different molecule. So when we remove protons, we are removing acidity. So that way we can try to go back to this point. And if we move to the opposite direction, let's say that your pH increased to 30.48, for example. Let's say that you have a lot of vomiting, and because we have hydrochloric acid in our stomach, you're losing a lot of acid through the vomit. So the concentration overall of hydrogen in your body is very low. So that means that your acidity is lowering, and your body is more alkaline. Uh, so you need something to try to compensate and go back there. So you need more hydrogen to move down, right? So you have too little hydrogens because you are losing it and through the vomit, and you need more hydrogen. So you need a weak you need a buffer to try to compensate that. So in this case, we have, again, this buffer is called a carbonic acid. And when it's necessary, this carbonic acid can donate the hydrogen that we need. So in this case, we have carbonic acid, and it's going to donate one proton, uh, and then it's going to convert in CO3. So you see here that the carbonic acid contains two hydrogens, and then when we need hydrogens because our pH is too high, this molecule kind of donate that that hydrogen that we need to increase our pH. That's the one of the example of how buffer works. And then finally, to complete this chapter, we need to go to organic compounds. And the main organic compounds that we're going to talk is sugars or carbohydrates, lipids, proteins, and nucleotides. I mentioned earlier when we were talking about the most abundant elements in the human body, and we mentioned organic compounds. So organic compound consists in a group of carbon atoms bounded with hydrogen, and those two elements has to be present in order to uh, in order to be an organic compound. Now, the important thing here about the um, compounds is the carbon shares electron with others elements, not just hydrogen. So carbon, it can share electrons with oxygen, it can share electrons with nitrogen, or with functional groups or different kind of groups. So, but the rule is that the carbon has to have at least one hydrogen atom in order to have or in order to be an organic compound. And I mentioned here functional groups. You don't have to really memorize these. Just know that the hydroxyl group, we mentioned this when we talk about pH and when we talk about bases, carboxyl groups, amino groups, and phenyl groups. And the important thing that I want to mention here is that if you look at the carbon uh, it contains 6 protons and it contains 6 electrons. And you see here at this point that the first electron shell is full with 2, but then the second one it just only contains 4. So that means that carbon it can take 4 electrons more in order to complete his valence shell. So those 4 elements can share with a molecule of um, hydrogen, for example, and they can form something that's called methane, which will be something like this. So, and you see 4 molecules because they has a space for 4 electrons. But as mentioned earlier, that doesn't has to be just hydrogen. This can be an oxygen, or this can be a nitrogen, or this can be one of those functional groups. And here we're going to go through these in more detail in the next slide to go through each of these. Let's begin with carbohydrates or sugars. The word carbohydrates means hydrate carbon, and as mentioned before, we need a molecule of hydrogen and a molecule of carbon to form an organic compound, and to form a carbohydrate or sugar, we need those two. And the other element that forms a carbohydrate is oxygen. And for your class, for your test, you only need to know that the carbohydrates, we have 3 types. We have monosaccharides, disaccharides, and polysaccharides. The word mono means just one, and the word di means two, and poly means many. So we're going to go and see each of those next. The monosaccharides that are important for the human life are those here. And we have basically 5. One of them are exos and the other are pentos. You really don't need to memorize them. Don't worry about the chemical structure. Just notice that the names of glucose, fructose, galactose, desoxyribose, and ribose, all of those sugars, all the carbohydrates, and O's. So if you see a molecule and you're not sure what it is, and if N's and O's, your best guess is this is a carbohydrate. So, and here the other thing that is important is that glucose, fructose, and galactose are sources of energy. Those two here, they're very important or they're very related and important in the DNA and RNA, which, as you probably know or heard, that DNA is that contains their genetic code. And the important part here is if you look those molecules, that's what I bring this image. They're pretty similar except for this oxygen here in this side. So that's why this molecule is called deoxyribose, because we don't have an oxygen that we have in the ribose. So that's why this is called deoxyribose. And the deoxyribose is the one that is present in the DNA, and the ribose is the one that is present in the RNA. Uh, Saccharides are also called simple sugars because that's the simple unit of a sugar. And the other thing is the base chemical equation is this. And just notice that um, usually in the glucose or monosaccharides, the same amount of carbons contains the same amount of oxygens, and hydrogens is double. So if you account all the carbons that are here, we're going to see that they're going to be equal to all the oxygens of this molecule, and the amount of hydrogen is double of the amount of carbon uh, or oxygen. Then we have disaccharides. I mentioned disaccharides means two. So when two monosaccharides or monomers link each other, we saw this when we were looking at water. Um, when we dehydrate, when we remove that, let's imagine that these two are separated. So this part, it contains a hydroxyl group, and this part contains a hydroxy group. So when we remove this hydroxyl group, and when we remove this hydrogen, we are going to form a molecule, a compound of water. So we are removing water. Therefore, this is called a dehydration, and it's called synthesis because we're forming a bigger molecule. So in this case, after we remove these, we have a whole molecule that it has a covalent bond here. Now, uh, if you see, and you don't have to remember exactly what a combination of monosaccharides form a disaccharide, but just know that disaccharides like sucrose, for example, is the table sugar that we have. And sucrose is formed when a molecule of glucose and a molecule of a compound of glucose and a compound of fructose linked together, they form sucrose, and that is the one that we got in the table sugar. Lactose, which is the main sugar in the milk, is formed by galactose and glucose, and that form lactose. And you know that sometimes you heard somebody saying that this person has lactose intolerance. It has to do that they don't have the enzyme that they need to break these bond apart, so they are lactose intolerant. And finally, if you put together two molecules of uh, glucose, you can form maltose, which is the malt sugar. And again, you can those reactions are reversible. So if you split monosaccharides, you split via hydrolysis. So you're gonna need water. So you're gonna break a water molecule, water compound, in order to break this bond here. So if you want to break it, you need a water to form the hydroxyl group and to form another hydroxy group with another here. So that is dehydration, and this last one is hydrolysis. And then lastly, we have the polysaccharides. Polysaccharides when we have more than two saccharides linked together. And the more important for our body are the starch, glycogen, and cellulose. Now, the starch and all the carbohydrates, we said that we need those for energy sources. So the starches, we can get all these polymers. Remember, the monomers means one, and polymers means a lot of sugars like this one here. There we can find those in plant-based food. Now, glycogen is also a polymer of glucose, and normally it's stored in tissue of animal, like or in the human, in the liver, or it can be stored in the muscle. And really, in animals, when they die, we don't have um, they're not too much in their liver. And for us, when we have a lot of sugar in our system, what we do is we through a dehydration synthesis, we start synthesizing glycogen, and we store our glycogen in our liver. And finally, cellulose or fiber, that the cellulose is part of the cell wall of green plants. It's not a digestible substance, and it has a good healthy properties um, with the digestive system. So you probably heard about that is good for you to eat fiber, and the reason is because if this is the intestine and we are eating glucose, we don't have the enzymes that are necessary to break this apart in the small compounds that we can absorb. So because we cannot break in the small part, we don't absorb those. And those molecules that doesn't absorb, it tends to attract water into the lumen of the intestine. And overall, when you have water, your intestine is more clean. Your That's why also is a fiber is good when you have constipation, because those molecules that we cannot absorb can attract water, and water in the lumen of the intestine just help with the flow and pass the materials through the rest of the intestine. Now let's talk about lipids. The key information that you need to know for your test is that all lipids, all fats are non-polar. And we said that when they're non-polar, they're also called hydrophobic, that they repel or they don't like water. So hydro is water, phobic they don't like. All the fats are hydrophobic. And all the lipids are transported through the bloodstream via proteins. So because we have the bloodstream here, and those molecules are not soluble in water, and most of their blood is water, they need to be in conjugation with protein. So when you have a lipid in a protein, you have something that's called lipoprotein. And a lipoprotein, probably if you go to your regular doctor, he might order tests like HDL, for example. Move this. HDL or LDL. And that's when you say, okay, we're going to check your cholesterol, we're going to check your HDL, LDL. That stands for low density lipoprotein. So what basically he's looking is how many cholesterol is in your blood has been or is circulating in your blood through those tests. And I'm not going to go in great detail here, but just know that the LDL is the bad cholesterol. And here we have the more important lipids that we're going to be discussing. We're going to see the triglycerides, we're going to see the phospholipid, steroids, and we're going to end the lipids with the prostaglandins. Triglyceride, as the word implies, tri means three, and glyceride is a molecule of glycerol. So you can see here in the picture that if we want to make a molecule of triglyceride, we're going to need a glycerol, and we're going to need three fatty acids. Now, through dehydration synthesis, we remove hydrogen and we remove hydroxyl groups, and we form water, and then we're going to have the triglyceride plus 3 molecules of water. So you can see here that tri means that we have 3 fatty acids. And triglyceride is also known as just fat. And we have we can divide triglycerides in saturated and unsaturated. And if you look here, basically the saturation is based on the fatty acid. So if you look here, this picture, we have a saturated. This part belongs to here, and is saturated when all the carbons are completely full by hydrogens. Now the unsaturated fatty acid is when they have a bond not with a hydrogen, like in this case. Now when you have this structure here, this is a rigid structure, so you're going to see that the saturated fats tends to be more solid in room temperature, like butter, for example, is an example of saturated fat. And then unsaturated fat, because they have this shape, you see that this structure is is not straight, it's less rigid, and they tends to be more liquid in the room temperature. So example of unsaturated fats are olive oil and omega-3 and some oil that comes from fish. And you probably know that, or if you don't know that, it's more healthy have unsaturated fats than saturated fats because of that reason, because the unsaturated tends to be more liquid and not solid like the saturated. And then lastly, we have the term trans and cis. And this mainly has to do with unsaturated uh, fatty acid. So the even though the just the natural unsaturated is more healthy than the saturated, when we artificially, when we add hydrogen to unsaturated fat, that is actually more unhealthy. So most of the time we're gonna see trans uh, fatty acid when we have artificial things like um, or let me give you this example here. So we have this unsaturated fatty acid. This distribution here of the hydrogen is called a cis. And this is good. This is healthy. This is the good unsaturated fatty acid. But sometimes artificially, uh, we change this hydrogen, and instead of putting there, we change it here. So just by that minimal change here, that makes this unsaturated a little bit more rigid. And in many like artificial fat that we consume, they use trans uh, unsaturated fatty acid. And if you look, for example, in your nutritional information and things that might contain, you're going to see the word trans, and that is more unhealthy than uh, the cis version, and the trans is even more unhealthy than saturated. And lastly, triglycerides are the major uh, fuel source of the body. So when we are sleeping or when we are not eating, the body uses triglycerides in order to get energy. Phospholipids. This is another kind of lipids, and phospho means that there's a phosphate group, and lipid that means that there's a fat. So the general, and I bring two pictures here just to demonstrate what's a phospholipid. Um, Here, the phospholipid has a polar head, that's one of their characteristics, and it has a non-polar tail. Remember those terms, polar and non-polar. Polar is hydrophilic, they like water. Non-polar is hydrophobic, they don't like water. And then other terms that you're going to see sometimes is lipophilic and lipophobic. So it's kind of the same. Lipophilic is something that dissolves in fat, and lipophobic is something that doesn't. So water is lipophobic and fat is hydrophobic. Um, and then here the phospholipids are important because they form or they're part of the cell membrane, and they compose the phospholipid bilayer, and we can see a picture of that. So to understand this picture, this is the cell membrane. You need to kind of know what's the structure of the phospholipid. So a phospholipid, this is the chemical structure, is composed by a phosphorus and a glycerol. So all this is the head, and all this part of the phospholipid is polar, so it is hydrophilic. And then we have the tail here, in which we have the fatty acid, and this part here is hydrophobic. Now you can see here that basically this is the same that we have here. And if you look at here, you can see how that looks like in the cell membrane. For now, main thing you need to know is that phospholipids, um, the main function, it has to do that with the cell membranes in the cell. Next, we have steroids. Steroids also are called sterols, but the most important for the human, for the structure and human function is the cholesterol. And first, the cholesterol is synthesized in the liver. It's an important component of the bile acids. Remember, the bile acid is what we need to break down fat when we eat. And then cholesterol also is a building block of many hormones, especially estrogen, progesterone. Those are examples, but there are other hormones that they're based on cholesterol. And that's another thing that is important in the clinical is that, for example, a woman who has been prescribed birth control, if you know birth control, basically you're taking estrogen and progesterone. So one of the tests that doctors will do before prescribing you a birth control will be a cholesterol panel. So they prescribe that because if you are taking estrogen and progesterone, your cholesterol level might increase. So the first test they do is like a baseline to see what's your cholesterol. And if you, after 6 months, for example, taking a birth control, your cholesterol remains the same, good, you will keep that birth control. But sometimes your cholesterol can increase because of birth control, and he might change that medication. Also, cholesterol is found in cell membranes, and as I mentioned before, uh, many of the fat, the cholesterol, triglycerides are transported through the bloodstream by proteins, and we mentioned already the HDL and the LDL. There are other important tests that your doctor might do. HDL stands for high density lipoprotein. It's called lipo because we have the lipid, and protein because we need protein in order to move the fat through the bloodstream. And we have the low density lipoprotein. We're going to finish lipids talking about prostaglandins. Don't worry about the structure again. This is just a representation that if you see something like this, you know at least that this belongs either to the cholesterol or to the lipids, but you're not going to have questions in your test that you need to, identify on the structure or something like that. So just don't worry about this. Just know that prostaglandins are coming from lipids, that they usually come from unsaturated fatty acid, and they're very important in blood regulation. Some of them are good because they can cause vasodilation, and they sensitize nerves to pain. So when we take medication for pain, they're called non-steroidal anti-inflammatories. We are basically blocking some of the prostaglandins that will cause pain. And then also prostaglandins plays a role in inflammation. And in our stomach, for example, prostaglandins are beneficial. They help to protect the cells that live in the stomach from the acid. So sometimes when you take ibuprofen, naproxen, etc., those are non-steroidal anti-inflammatory medications, because you're blocking those prostaglandins, you have a risk that you have too little prostaglandins, and that can be a little bit hard for your stomach. So many times you're going to see or heard that if you take ibuprofen or if you take naproxen or those kind of medication, one of the side effects is you can have gastric ulcers or you can have a stomach pain, and it's because the reduction of the prostaglandins there. Now let's finish this talking about the proteins and lastly nucleotides. Proteins are organic compounds. You can see in this picture that it contains carbon and contains hydrogen. You also all the proteins are formed by amino acids, and multiple amino acids form peptides, and multiple peptides form proteins. Now, those amino acids are linked together through what we know as a peptide bond. And the important thing that you know here is that we have amino acids, which sometimes they're polar, and some of them they might be non-polar. So we have both here. We don't know, depending on which amino acid we're talking about. Some of them might dissolve in water or be hydrophilic, and some of them might be hydrophobic. The important thing that proteins are the components of enzymes. We mentioned that in chemical reaction we use enzymes to increase the rate of the chemical reaction in the body. We know that the proteins are part of the antibodies, and antibodies plays a role in immunity, and many emitters are made of proteins, and many hormones also are protein based. All the proteins contains nitrogen, which is this one, and this nitrogen is the part of the molecule that is nonpolar. And this part here, you can see the carboxyl group. It contains a lot of oxygen, so this is a polar. Remember that every time that you see oxygen, uh, oxygen tends to pull negative charge, and because this is will be kind of the negative side of this amino acid. This is the polar side, and sometimes this is the non-polar side. And finally, we say that the building blocks for proteins are amino acid. We have in the body is 20 amino acids that are basically important, and just 9 of them cannot be synthesized. So we need 9 of them getting through our food or diet. Other important aspect that is that we need to take in consideration is the shape of the proteins. And we're going to see that the shape of the protein is essential to the function of the protein. We basically have uh, 4 major protein structures. So the first one is this one. This is the primary structure, and we have here A1, A2. A stands for amino acid, so we have an amino acid one, then another amino acid, a third, four, and so forth. And between them, we have the peptide bond. And when we have this kind of protein, that's a primary structure. Normally, we don't have too much primary structure. We usually have uh, proteins that are a little bit more complex, like this one. This is a secondary. And here in the secondary, we have some that have like alpha helix shape. And you see here that this protein has this kind of spiral shape, or they can have uh, these this other shape that is called the beta place sheets. The important part here is that I want you to put attention in those little dots that link together this amino acid, for example. And I put in here, I don't know if you can read it, but this is hydrogen. So this is a hydrogen bond. And as we mentioned earlier, hydrogen bonds are usually weak. And for example, if you put if you increase the temperature, those bonds can break apart. And those proteins that are folded in this shape, if you break these bonds, they might lose the shape. And if as you read initially, they say the shape of the protein is essential for the function. So you can imagine that, for example, we have this protein here that has this shape, but then you break these hydrogen bonds here, and instead of being this shape, it start being this shape, because you break here, this protein might be not functional anymore. And then we have other more complex kind of proteins, like this kind is called the tertiary. And we can see here, or we're going to see later, that this is also called the globulin. And finally, when we have three or more or two or more global in shape, we can have a quaternary structure. And this is an example of hemoglobin. And hemoglobin is made by four globulin proteins. Here we got the globular proteins. I said that it has like a sphere shape, and we can see that when we have a globular, you have to know that we are talking about tertiary structure. Um, the vast majority of the enzymes are tertiary, and most of them, has this globular shape. Other thing that is important is when I mentioned that when we break those bonds in proteins, the shape of the molecule can change. And when that happens, when we break those bonds, that is called denaturization or denaturation. And that is a change in the structure of a molecule through physical, like heat, for example, or chemical means. So the denatured proteins lose the shape and therefore their function. And those changes can be reversible and sometimes it can be irreversible. Let's finish this talking about nucleotides. So to conclude this chapter, the nucleotides that we're gonna be talking about is about the nucleic acid and then the nucleotide ATP. Very quick here. The only thing that you need to know is that the main nucleotides or the nucleotides are the place where the genetic information is stored. And that all this DNA and genetic information is contained in the cell and is contained in the nucleus. And if you took the lab number 2, you remember seeing mitosis and the chromosomes, so we're going to see images of that. Here, the important thing is that that some of these nucleotides contains sugars and contain the oxyribose and ribose. And we mentioned that the ribose belongs to the RNA, the desoxyribose belongs to the DNA. The main DNA bases, you really don't need to, you might need to just to know that we have these four: adenine, cytosine, guanine, and thymine in the DNA. And then the only difference between the DNA bases that we have in the DNA and the ones that we have in the RNA is uracil. So instead of having thymine, we have uracil. And those DNA bases are also called nitrogenous bases. They're the ones that are link each other. And most of the time, you're going to see this a picture or representation of the DNA. And you're going to see that they form pairs. And always adenine is always together with thymine. And guanine is always linked to cytosine, as you can see here in the picture. And then I brought this picture just so you have an idea what the chromosome is. And if you try to go even more small, you can see that you're gonna get in the point where you can see those blue lines here, and all those blue lines are the DNA. And if you look at the DNA, you can see those letters here. The letters represent the bases. So the A is for adenine, the T is for thymine, G is for guanine, and C is for cytosine. And I'm not going to get in way more detail. You're going to see this in next chapter, how we create proteins through these DNA. The last part of this chapter is the ATP, the nuclear ATP stands for adenosine triphosphate. And we can see here in the picture that we have a group here is adenine, and we have here the ribose, which is a sugar, but all these together is called adenosine. And the adenosine, when we add a phosphate group like this one, we have AMP, or adenosine monophosphate, when we only have just one. If we have two, we have ATP, and when we have three, we have ATP. And in each of those bonds, as mentioned earlier, there are high energy. There's high energy bonds, and when we break those apart, energy is released. So other thing that you have to know is that glucose is closely related to formation of ATP. And with that, we conclude the chapter 2, the chemical level of organization.